Good day, everybody. This is Mike Van Giem at Hammond Power Solutions. I'm the Director of North American Marketing. Joining me today will be Sumant Bashist. Sumant will be part of the panelists here that we'll be talking about. Today's topic will be transformer technologies, liquid versus dry. Today we will actually be giving two separate presentations. The first presentation will be comparing liquid versus dry type technology. And the second presentation will be talking about some of the specification differences between the two products. I'd like to just quick introduce Hammond Power Solutions. We are North America's largest manufacturer of dry type transformers. We do have a manufacturing plant that builds liquid type, but we do not support liquid type transformers currently in the North American market. The goal today is to give a balanced examples between the two technologies, which are liquid and dry type, and we'll go into details shortly. One of the big reasons why we're having this presentation right now is because this topic has become very topical, mainly because lead times for power transformers have gone out, and in some cases we're seeing lead times for liquid type transformers at 1 and even 2 years. As a result, some people are looking for alternatives, and one of the alternatives people are looking at is dry type. And one of the things that we want to get across today is that both technologies are very good technologies, and there are pluses and minuses for both technologies. However, there is no dry type equivalent for a liquid cooled transformer, and there's no liquid cooled equivalent to a dry type transformer. They both can be used oftentimes in the same applications, but things like site preparation and specifications definitely have to be adapted to both technologies. We'll start off by comparing how the two technologies really kind of stack up against each other. And again, one of the things that we'll be talking about is we're making some general statements about both technologies. When we talk about liquid versus dry type transformers, we're going to be giving some examples of where one technology may have some advantages over the other technology. Keep in mind that either technology can probably overcome these disadvantages, but in a lot of cases it may be something that is not a general design principle. It may add significant cost. So again, we're going to be talking about how the general specifications stack up, but you will be able to find examples in both technologies where they can probably overcome these with no problem, but again, may take a lot of money or some additional design stuff that isn't what we would term as typical. So at the end of this presentation, we're hoping that everybody has a good appreciation for the differences between both dry type and liquid type technologies. So let's start off with liquid filled transformers. They are called liquid filled because that is exactly what they are. We build a transformer, and if you compare what a core and coil, or what the core and coils look like between a liquid and dry type, they're very similar. I mean, if you put up either a dry type core and coil or a liquid core and coil, you will recognize it as a core and coil, although there are some construction differences we'll talk about. The big difference, though, is that with a liquid filled transformer, they take the core and coil, they put it into a tank. Basically, it's called for what it is, a fuel tank, and they then submerge that transformer in a liquid. Typically, people have referred to it as oil, and the oils range anything from something that would be, termed diesel fuel, to more modern stuff would use mineral oils, and even more modern designs would use what we call ester oils, which are a vegetable-based oil or some type of silicon, liquid silicon technology. And again, the entire transformer is submerged in this liquid. The liquid is obviously non-conductive, and the heat that the transformer generates is then transferred to the liquid, which is then transferred to the, we'll call it the tank walls and or cooling fins. So in the case here, the picture we're showing here is really what we term a high voltage transformer versus a medium voltage transformer. And high voltage transformers, as we will talk about soon here, really are the domain of liquid filled. Medium voltage or dry type transformers really are only applicable to applications that are 44 kV and below. Anything higher than that, and you're really probably looking at liquid filled. There are some transformer manufacturers that will go up and state will go up to 69 kV class, but for the most part, anything above 44 kV will be a liquid filled transformer. When the transformers are cooled, and the cooling fins here, there may be some pumps or there may be natural convection flow for those fins to help dissipate the heat. In some cases, the fins are very small and they're just trying to extend the surface area of the enclosure. So the fins have different technologies, but you can also think of them as a radiator for an oil transformer, and it is an additional thing that does have to be maintained and could be damaged or could cause a leak as well. With a dry type transformer, the transformer is, well, as we say, it's surrounded by air. And the heat that the transformer generates and needs to be cooled by is directly transferred to the air that circulates around it. And in this case, you can see the core and coils. There's two really main types of medium voltage transformers, what we call VPI and another one we call cast resin. Some people call it cast coil. The difference is really here is how thick is the resin coating, or how thick is that varnish that some people talk about that covers the core and coils. So when we look at a liquid filled transformer, the main insulation component is the liquid that surrounds it. In a dry type transformer, the main insulation components actually are the air gaps, and air is not as effective of an insulator as the liquids. So we will have to have larger air gaps within the transformer. In addition to the air gaps, we also coat the transformer in a liquid coating. A vacuum pressure impregnation transformer, basically a transformer, the coils are submerged into a vat. The vat has a vacuum pulled in it, so there's no air bubbles. Then we use the vacuum to submerge the transformer in the liquid varnish. We'll call it generic varnish, but it's nothing to do with the varnishes you would put on furniture, for instance. And the transformer coil is fully submerged, and then the vessel is then pressurized to further push that liquid into it. And there might be 2 or 3 or 4 or more coatings of that put on. The other type is what we call solid cast, where the core and coil is actually put into a mold, and the entire mold is filled with an epoxy resin and hardened. And this provides a much thicker coating. The other ones where we have just the VPI portion, the majority of the insulation system really is based upon air gaps. When we do the cast resin, the majority of the insulation system, great majority, is really based upon the resin material itself. And in some ways, it'd be more analogous to a liquid filled transformer, but again, very differences in construction and performance. So let's talk about insulation systems. With a dry type transformer, we generally use Nomex, and there are a couple other products that are similar to Nomex. But again, it's a very expensive, a very high-tech, very effective way of insulating a transformer that will last decades. Nomex is very strong. It's, as we say, it's what they, firefighters, when those big suits that they wear that are flame resistant, they're made out of Nomex. And it has, really good properties for both being able to handle long-term heat and being able to insulate. In addition, we also use air gaps. The issue is, and everybody's seen lightning, at a certain point, the dielectric constant of air tends to lose some effectiveness. And generally for VPI transformers, that would be up to about 46 kV class. Again, we've seen some cast transformers claim to go up to 69 kV class, but for the most part, we're looking at 46 kV and below, and up to 250,000 volts or 250 kV BIL ratings. Anything above that, and you're probably going to be looking at liquid. Now, liquid fill typically uses what we call craft paper. It's just thick paper. And paper in itself is not a good insulator, but when you soak it in oil, it works very well. It's very effective. And because of the surface area and because of how the transformers are cooled, liquid filled transformers tend to run cooler. Doesn't mean that they're that much more highly efficient than dry type, but it has a lot to do with the surface area and the cooling fins and stuff like that. And they have to run cooler because they're using paper. So at temperatures where Nomex would, it'd be like a fall day, paper starts to deteriorate. So they have to run the transformers cooler as well in order to work it. But as long as both transformers are properly designed and cooled, they both should supply you with decades of solid use. When we talk about overload capabilities, dry type does have an advantage. We can do lower temperature rise transformers than what you would typically see with oil, or that oil would allow. And by having these lower temperature rise transformers, we can do two things. We can put them into hotter environments without derating. They can also give us additional capacity, provided we maintain the standard environmental temperatures. As a result, depending on if it's a VPI design or a cast coil design, we can get somewhere between 15 and 30% additional continuous overcapacity with a dry type transformer. And if we add fan cooling, we can get between 33 and 50% additional capacity over the base nameplate. With liquid filled transformers, while they run cooler, they have less ability to do overload conditions. And typically the most common one would be 15% overload capacity. And fan cooling can give you an additional potential 15% additional capacity. So in some cases, this is actually a valuable tool to understand, because in some cases we do see people greatly oversizing the liquid filled transformer because of either the environmental temperatures or potential for brief overloads. And as a result, the kVA differences between liquid and dry type may be calculated differently. We hope not, but all transformers could experience a short circuit event. When a short circuit event occurs, we are hoping that the fuses or circuit breakers, whatever the overload technology is, will clear the fault quickly. However, in between when that fault is cleared and when the overload occurs, the coils will be experiencing huge increases in current. We're not really worried about the heat for that short-term duration, provided that the breakers and fuses are properly set up. However, that current also creates an amazing amount of mechanical forces within those wires, and those wires could deform. They can break, they can cause the coils to fail. With dry type transformers, generally speaking, the construction of them, the actual physical construction and the way we use those varnishes to kind of glue and hold everything together does provide some significant mechanical bracing in the event of a short circuit that you typically don't have in a liquid transformer or liquid cooled transformer. Therefore, a dry type transformer does have some advantages in being able to withstand short circuit conditions. Flammability characteristics are important. With dry type transformers, there is very little, if any, ability to burn anything. About the only thing that might be able to really combust within a dry type transformer might be the varnish, depending on what type of varnish that we're using. And that would be less than 5% of the total mass of the transformer. So again, and that tends to be self-extinguishing even then. So there is very little concern of flammability with a dry type transformer. If it does fail, you'll probably have some release of smoke, but we're not worried about burning down a building or starting other fires. Obviously, we have to be very concerned during a short circuit, for instance, to make sure that there's nobody by the transformer, because short circuit conditions can send out, there's still gases and stuff like that. So we're not saying you want to be staying next to a transformer by any stretch of imagination, dry or liquid, if it fails. But the failure mode of a dry type is much more benign than a liquid filled. Liquid filled transformers do, the liquid typically can provide additional burning mass, and it can be significant. Now, modern liquids tend to have incredibly high flash points, 155, 170 C. Some of the ester oils are double that. However, in the event of a building fire, those liquids can still provide burning mass. They still have to be contained in the event of a leak. So liquid-filled transformers can, have a potential for catastrophic damage during ignitions or leaks. Leaking is also a concern. We'll go about it later, because even if the leak just results in a puddle and a leak that does not actually cause a fire, the leak still has to be contained. Installation is probably one of the biggest concerns when somebody comes and says, hey, let's look at options. I have a liquid filled transformer. I want to look for options with a dry type transformer. And the issue here is that the transformers really are installed differently. For indoor applications, there isn't a lot of additional prep work that we need to do with a dry type transformer if it's going into a standard electrical room. Okay, dry type transformers provide flexible cable entry points. So basically, I can come in from either side, top, bottom, or sorry, either in, top, bottom, sometimes from the sides, if I'm trying to come into a dry type transformer and either get power out of it or bring power into it. So it's very flexible for things like cabling or conduit. And we don't need a fire resistant room. So a general room construction for an electric room, for instance, is more than adequate for a dry type transformer. Now, when we install a dry type transformer outside, there are a couple concerns that we have. We would like to have that unit installed in an area that's secure from the general public, because there are probably vent holes and stuff like that within the transformer. Generally, the transformer won't be as heavy, won't require as much of a concrete pad. However, a dry type transformer is cooled by air, and inherently there is going to be an air transformer. So if the area is, has a lot of dust, especially if it's conductive dust, like a coal plant or something like that, that could be a big concern. We can build transformers that are what we would call non-ventilated, but those tend to be significantly larger and more costly than a ventilated unit. With a liquid filled transformer, if I install it indoors, I do have to take certain precautions. Even if I'm using an ester oil, let's say, that has a high flash point, may not need to have a fire resistant room depending upon the local codes, I still have to be able to contain all that liquid, either with a separate box that surrounds the transformer, or I would have to dike the whole room. So, and this would also be, let's say if I install a transformer on a roof or something like that, we have to be concerned if that oil is leaking. Again, not all of the modern stuff like ester oils require a full vault, but for the most part, there is definitely some additional installation cost and lack of flexibility if I'm using a liquid filled transformer. And again, a liquid filled transformer, typically I can only come in on the front of the transformer where I have specifically that wiring compartment. I have less options if I'm bringing in buswork or cable. Now, for outdoor applications, a liquid filled transformer by its very nature is an enclosed system. There is, or should be very little of any transfer of outside air to interior to the tank. And for dusty, nasty environments, sometimes a liquid filled transformer has advantages. For instance, if I'm going to put a transformer on top of a 20-foot power pole, one would think maybe a dry type would have some advantages because it would be lighter because of the lack of liquid. But on the other hand, putting an enclosed, hermetically sealed metal can on top of a pole that could be difficult to go and check is probably a better solution. That's why, for the most part, all pole top transformers are liquid filled. Environmental concerns are an important and growing concern. Dry type transformers, for the most part, are environmentally safe. There really is no risk for a dry type transformer. We're not really concerned about anything when we install it in an environmentally sensitive area. Liquid filled, however, does present some problems. Depending on what the liquid is, again, some of the least expensive liquids would be more equivalent to, let's say, diesel fuel, or more commonly, at least in North America, mineral oil. Those still provide some environmental risk, environmental assessments, insurance. Depending upon the size of the transformer and how much liquid is in there, we may also have to provide some type of, even outdoors, we'd have to provide some type of basin to catch the liquid should it leak out. If the liquid leaks out, even if it's somewhat benign, let's say that's an ester oil that is, might be a peanut-based or some other type of vegetable-based oil, even in those cases, environmental reports would still have to be fired. Some containment would have to be done if it spills on the ground. So there are environmental concerns with liquid filled transformers that simply don't exist with dry type transformers. Maintenance is also very different. Obviously, with the dry type, I can de-energize the transformer, and I can physically go in and inspect the coils. I can test them easily. If I need to repair something in a coil, provided I can, whether it's a loose fitting or something like that, I generally can get to it fairly easily. I don't have to drain any oil out, and I can deal with it. Installation-wise, dry type units typically weigh less, and their enclosures can be removed. This is a really important consideration, especially interior. I can take a dry type transformer, I can completely disassemble the enclosure, I can bring the core and coil through a door and then reassemble the enclosure inside. With a liquid filled, I don't have that option. It's a welded steel enclosure, and it may be some difficulty getting around corners or through doors. Typical lead times. Okay, this is actually a little bit old. So typical lead times, I guess they could be 4 weeks right now, but if we're talking power transformers, we might be talking closer to the 13, 15-week period right now, depending upon the size. When I go to liquid filled transformers, typically for preventive maintenance, because I can't directly visually inspect the transformers, I'm taking samples of the oil periodically and sending those in for testing. If for some reason I need to repair a core and coil issue, I will have to drain the tank. If a bushing starts to leak, I will probably have to drain the tank in order to fix that. So maintenance issues become much more intense and problematic. And again, I can't directly inspect the core and coil for damage. Installation, liquid cooled transformers often weigh more. The enclosures can't be disassembled. You might be able to move it in without the oil, but then you'd have to bring in oil later on to fill it up. And typical lead times, as we've discussed, we've seen some lead times now of over a year, in some cases approaching 2 years for liquid filled transformers. And when we talk about those lead times, really we're talking about what we call medium voltage transformers. I believe high voltage transformers, lead times could be even longer than that. Close coupling to switchgear, dry type has some advantages. You can come in from the top, bottoms, ends, sometimes from the sides. We can close couple in a lot of different ways and configurations. With liquid filled, typically I have a wiring compartment in the front, and I can only come in from a couple of directions from that front mounted wiring compartment. I am much more limited into how I can bring in cabling or busing. Sound level. Liquid filled transformers have an advantage. We can build low audible noise transformers, but it's not our typical construction. There are things that we have to do. By taking the transformer's core and coil and surrounding it in a liquid, that does deaden the noise. Again, if you are swimming and underwater, people screaming on top of the water sound a lot quieter than if you're above it. Same thing happens with liquid filled transformers. However, liquid filled transformers often employ things like cooling fans. Remember earlier we talked about being able to build low temperature rise transformers. Because liquid filled has a lot fewer options, they may be more applicable to employ cooling fans in certain situations, and now they are more noisy. So it does depend upon the application. Energy efficiency, liquid filled transformers do have an advantage, at least especially for those that are covered by what we call the DOE regulations, or in Canada, Narcan. Generally speaking, liquid filled transformers are going to be slightly more efficient. The requirements by either the US or Canadian Departments of Energy are more stringent for liquid filled transformers, and as a result, they will have slightly better efficiency and a little lower operating cost as a result. Now, we can achieve higher efficiencies with dry type. However, again, that typically involves additional cost. So again, we're talking about just based upon how the transformers are built per the current regulations. Overall footprint is an interesting topic, and we've seen some liquid fill manufacturers say that their footprint is a lot smaller than dry type. The issue with some of those claims is you got to be careful. When they're talking about footprint, oftentimes they may be talking about the part of the transformer that physically is attached to the concrete, let's say. But they may not be taking into account the fact that I've got 3 feet of cooling fins hanging off the back of the transformer. And while those don't mount directly to the ground, and technically there's no footprint below that I have to have something to mount it to, they still take up room. So again, when we look at the footprint of liquid versus dry, we include the cooling fins, we do see some advantages with liquid filled. Typically, it's a little more apparent in the larger sizes. Smaller, you might actually see some advantages. I'm sorry, in the larger sizes, you might see some advantages in the dry type. In the smaller sizes, you might see some advantages in the liquid filled. So it's kind of neutral. It will depend upon the situation. It will depend upon if it's indoor or outdoor. It will depend upon the temperature rise and overload capabilities of that particular application in order for you to decide which may have an advantage or not. You really have to get more into the details to figure out ideally which one would have the smaller footprint. It's not always apparent. Cost comparisons can be difficult. So a few things. Generally speaking, liquid filled transformers will cost less per kVA than dry type. Okay, so, and how that cost is attributed can be very difficult. A lot of the cost potentially has to do with what the BIL rating is, what the voltage rating is, and what type of liquid you are using. If you are going to be using especially a modern ester oil or a silicon fluid, those will cost significantly more per kVA than, let's say, less expensive mineral oil or even oils that are less benign than that. So the initial cost for dry type tends to be more for the actual transformer. However, site preparation for liquid filled tends to be quite a bit more. And if we have to do fire suppression, oil containment, additional permits, if I had to build a vault type room, the cost that we have here for site preparation could be even several times what we have listed here. So one of the things, again, when we talk about, if somebody is installing or has specified a liquid transformer and now they want a dry type equivalent, again, there is no dry type equivalent. They don't, there isn't a dry type equivalent. There's a whole bunch of stuff that has to be redone, and we'll go into the specifications later. But the other big thing is the site preparation. How is the site prepared? And in order to take some of the advantages of the two designs, with liquid filled, I might have a lower initial cost for a transformer, but higher site preparation cost. With a dry type, I might have a higher initial cost for the transformer, but I might have additional site preparation cost. And you have to be able to adjust both of those to achieve the full advantage of either design. In addition, there's additional maintenance cost. You know, if you're going to take a liquid transformer, shut it down, sample the oil, send out the oil for testing, get the sample back, there's definitely a cost there versus, you know, de-energizing the transformer and inspecting the coils visually, which you can do with the dry type. Then there's additional insurance costs. Oftentimes there's additional insurance costs for liquid filled, especially if it's within a building. So when we talk about the total cost of ownership, it becomes a little more difficult to discuss. Dry type transformers will have higher losses. So again, we'll have a little more electrical costs, but then things like insurance, testing, maintenance might be lower with a dry type. So again, where the advantage would lie between the two designs typically is much, you know, you can't make a blanket statement that says one is better than the other in all cases. You really have to kind of look at the overall application where it's installed. However, you know, especially if you talk about interior designs, a lot of times a dry type transformer will have some additional cost of ownership advantages over a liquid filled. So we have our cute little charts here. This kind of shows where there's neutral, where there's advantages to liquid filled, and where there's advantages to dry type transformers. Again, what we're seeing here in a lot of cases is these are typical parameters. We might be able to overcome these parameters with either design, but it may go a little bit over typical design. And some of these judgments where we got the arrow pointed, if it's better one way or another, may, you know, always be always might have additional dependencies. So this is meant to be kind of a quick reference chart, but how you may or may not have an advantage in your particular design will be application oriented. Okay, we haven't had a lot of questions. I see one hand raised, but I'm going to address the raised hand at the end of the presentations. This concludes our first presentation, where we were comparing liquid and dry type technologies. The next presentation that I'm going to move to is when we talk about converting a liquid-filled transformer to a dry type specification. What has to be done in order for us to accomplish that? And again, what we're trying to say is that the basic operation of liquid and dry type transformers, it's the same. A lot of times we're changing voltage, we're providing, possibly some harmonic mitigation depending on how the phases are arranged. We might be obviously providing short circuit mitigation, stuff like that. But the thing to remember is we're kind of comparing helicopters and airplanes. They both fly, they both do the same job. They might both be able to do the same job effectively, but we just need to make sure that we're specifying the stuff correctly. And again, one of the keys we have here is that when somebody calls and says, hey, I have a liquid-filled transformer, can you give me the dry type equivalent? We can't. That is not possible. Okay, there will be a whole bunch of exceptions. And the best way, if you want to consider a dry type alternative, is to come up with a dry type specification that best meets the needs for your application, knowing that oftentimes you may also have to address site installation in order to get the true advantage of either design. So dry type transformers. Right now we're looking at applications below 44 kV. The BIL, which is the basic impulse level, the highest voltage level that transformer can hit by a knot arc, we're looking at 250,000 volts, 250 kV. For dry type. Typically, dry type transformers will be 40 MVA and below. That's a pretty big transformer. But when we start talking about 100 MVA, main power transformers, typically high voltage units, those are really the domain of liquid-filled transformers. Pole-mounted units, we already addressed that earlier in our conversations. And if there's areas that are accessible to the general public, liquid-filled transformers often have some advantages. As an example, behind our house in our subdivision here, we have a little green transformer case. It's liquid-filled. It's about the size of half of an oven. It's only about 2.5 feet tall. Kids go climbing on it. That is a hermetically sealed unit. And I don't like the kids climbing on it. In fact, I take them off. They shouldn't be. But a completely ventilated unit probably is not a good idea to install in an application like that. That's, again, so it has a lot of accessibility to the general public. So when we look at a specification for liquid filled, sometimes the transformer specification doesn't actually say liquid filled, or sometimes it does, but you have to kind of get into it. There are some clues though that will key us into liquid filled. When we hear the words bushing wells, anything that says bushing, anything that says drain plug or fill plug, again, these are typically associated with liquid filled units. That will tell us it's a liquid filled transformer specification. Manual load break switches are, again, something that's more common within the transformers. There's certain things that I can do with a switch that's also surrounded by the oil that the transformer is using that I can't do as easily if it is a what we call an air switch, a normal switch that operates in the air versus something that is submerged in oil. Obviously, things like liquid level gauge, pressure gauges, these all indicate that I'm using some type of a liquid. Valves. FM Global Approved is a insurance agency that does a lot of stuff with commercial properties, especially in North America. They tend to have certain specifications for liquid filled transformers. So having something that might meet their overall specifications will help standardize what the insurance policy is for that area. We will see certain IEEE standards that are specific to liquid filled versus dry type. Again, we might see things like dielectric coolant, less flammable fluid, under oil or oil immersed. all of these terms and conditions are really reflective of a liquid-filled transformer. And by the way, there is no dry type equivalent. So when somebody, again, hands us an oil spec, we can't meet this. Probably don't need them, but again, can't meet it. So there's a couple things. We sometimes run into a situation where a specification says no load tap changers. This is where you can install a relatively simple mechanical tap changer in the actual oil that the transformer itself is submerged in. And by twisting a dial with a wrench or something like that, I can change the taps within the liquid. And there's some advantages to doing this. I can do this relatively inexpensively and easily because I'm not worried about arcing where I would be if the switch was just in air. And I also don't have to pull all those taps out with additional bushings through the transformer. So there's less points where that transformer can leak. Okay, this is not a bad solution for a liquid-filled transformer. With a dry type, we don't need a rotary tap changer. It's a no-load tap changer. Well, if the transformer is under a low load, it's a dry type, I simply go and physically remove the bolts on the taps and change them. So when some people say I want a no-load tap changer, that's because I have a problem bringing additional wires through the transformer sidewall and potential for leaks that I don't want to encounter, and I can fix that. I can mitigate that by having a no-load tap changer submerged in the oil. I don't need to do it with a dry type. Okay, and we sometimes have people say, well, I still want the no-load tap changer. Well, in order for us to put contactors in that can do that, becomes a very complex and expensive means to do for a dry type transformer. Again, we would just say, change the taps. By its nature, liquid-filled transformers are sealed in a non-accessible, non-ventilated enclosure. Dry type transformers, by their very nature, are ventilated. And again, those ventilation holes provide us with some concerns that the transformer is accessible to the general public. Efficiency, there are different efficiency levels for liquid-filled versus dry type. The efficiency levels generally for a liquid-filled, actually not generally, always for liquid-filled, will be a little bit better, a little bit higher efficiency levels than the dry type. And we've addressed that earlier. Terminations. Liquid-filled have fewer options for terminations. Again, generally you have a front-mounted wiring compartment, and all terminations have to be within certain locations in that small wiring compartment. With a dry type transformer, you have much larger ability to bring in stuff from below, from the roof, from the sides than you do with the liquid filled. So again, a lot more flexible in the cabling and busing methods for a dry type. Temperature rises we already addressed. We have a lot of additional temperature rise options and overload options for dry type. As a result, the kVA sizes for dry type and liquid filled may not necessarily match. I may be able to do something, with 1,000 kVA dry type transformer, 115 degree C temperature rise, which is a low temperature rise transformer, that maybe somebody specified in a 1,200 kVA liquid filled because they didn't have that low temperature rise flexibility, or as much of that flexibility with a dry type transformer. Dead front construction is very typical with liquid filled. Oftentimes it might be part of a larger utility requirement, which has to, which could be very important within the installation of that transformer. Dry type transformers can be built with a dead front construction. It's not as typical as it is with liquid fill. We have done it, we do it all the time. But again, it's something that is a little bit different. And you have to be careful when you say dead front construction. Typically what you do with a dry type is the way we would interpret that is we bring all the connection points into a separate terminal, often called an air terminal chamber. And then we have a dead front construction on that specific air terminal chamber. However, there are additional access points to the main transformer, and those are typically open because we would have some difficulty in blocking those off with some type of a dead front construction for the cooling characteristics. Again, you can do it, but it's not really the way most people would. Sound levels, again, liquid filled will be a little bit quieter than dry type by the very nature that the corn coil is submerged in the liquid, and that helps deaden the sound. You can do lower audible noise transformers with dry type. but they tend to cost a little bit more, be a little bit bigger. However, because liquid filled transformers don't have all of the temperature rise options that dry type do, oftentimes with liquid filled, you might be more common to employ cooling fans, which can greatly increase the dB level of that particular transformer. There's different terms. Liquid filled has ONAN, ONAF, OF, AF, OF, WF. Those aren't directly attributable to the terminology that we use for dry type transformers. So if we see an ONAN, we don't necessarily have a direct equivalent. I guess the closest one for us would probably be ANN, but again, different terms, and in some cases different methods to do the cooling. I'm not going to go into all of these, but again, just be aware when we see these cooling terms that start with an O on the left-hand side of this chart, we know pretty much that this was a liquid-filled specification. A lot of times you run into questions on the insulation system, and by their very nature, liquid-filled transformers run cooler, and they have to run cooler because of the insulation system that they use. And they have some, methods to cool themselves differently than a dry type transformer does. However, the insulation systems for a dry type transformer are much, much more robust. So really, when we talk about, the temperature rise, what temperature that transformer runs at, you do not need to have an equivalent, very ultra low temperature rise for the dry type. The insulation system can handle much higher transformers and still give you easily the equivalent lifetime of use that an oil does. So, we do have to change and make sure that the temperature rise requests are equivalent. Otherwise, we will be building a much, much lower temperature rise transformer with a dry type than is probably needed, and the cost and size will escalate accordingly. So again, we've had some other graphs here in the temperature rise options. You can see here that depending on the temperature rise, an 80°C temperature rise transformer, which is a common option in dry type, can actually handle an ambient temperature hotter than the boiling point of water. You don't have those options with a liquid filled transformer. So depending on what ambient temperature you're going to run that transformer at, I can either run it at higher ambient temperatures or I can get some additional capacity. When we look at the additional capacity, you can see that that's at a 30°C average ambient versus the column just to the left of that, which has higher average ambience. So again, a lot of additional temperature rise options with dry type that can affect the design protocols and the equivalent kVA that you would be specifying and using. Site preparation is a big one. With liquid filled transformers, there might be things like spill containment, fire suppression, drainage, environmental assessments and additional permitting, transformer vaults, limited in busing and connection vectors that will result in some differences in design that may not be any consideration or any issue for a dry type. If you want to get the best value out of a dry type versus a liquid filled, you really have to compare the application, and you have to come up with a dry type specification and site preparation work specific to that dry type transformer to get the true value out of it. If you're looking just at the cost of the two transformers and not including some of these additional preparation costs, a lot of times it'd be more favorable to a liquid filled transformer. When you take these other issues in consideration, that would adjust a lot of times where your cost and benefit analysis would bring you. So final notes. We do have, Hammond does build a lot of medium voltage transformers. We believe we are the largest medium voltage transformer manufacturer in North America, one of the largest in the world. We do have both a VPI, Millennium series, and a cast coil, our EnduraCast coil for the North American markets. So we can supply transformers, And when you look at the voltages and the max kVAs that I've given earlier in these presentations, those would be equivalent to what our maximum kVAs would be as well, and voltages and BIL levels. Other manufacturers that build this may have much lower capabilities. Our biggest thing here is that if you do want to consider a dry type transformer for what we would normally, maybe in the past have specified a liquid filled for, there's a lot of different design considerations you have to make to get the true advantage. In a lot of cases, there's some great advantages to liquid filled, and there's some applications that, there's some great advantages, to liquid filled, there's some great advantages to dry type. We would like to, if you have questions, you can call us. We're more happy to work with you. We will try and give you a halfway decent assessment. Where we have often issues with is when somebody just gives us a liquid filled transformer specification, says, give me a dry type equivalent. Oftentimes we have to reject those because we simply can't. That doesn't exist in a practical sense. And again, the goal here is to make sure everybody has an appreciation for that. And if you do want to approach that, how do you approach that problem effectively to get the full value for you? All right, this concludes our presentation. I hope you found it informative. I would now like to open it up if there are any questions for the audience. Are all lead times and cost updated? The lead times and cost, good question, because we've seen some massive changes in cost and lead times. No, these costs, the calculations that we did actually were done about 12 months ago. However, to the best of our knowledge, the cost for both liquid and dry type have scaled relatively the same. So while the cost may be a little bit different, the end result would be, for the most part, equivalent today as it was a year ago. The calculations that we did for the energy efficiency should be pretty apparent today. The cost of electricity has not changed that much in the past 12 months. Leads, and I had a question here, are lead times equivalent today? Yeah, I mean, lead times are still highly dependent upon what the specifications are. So, could there be a transformer in dry type that could be, longer? I think I had 13 weeks on there. I think I said 13 to 15. Could there be a transformer that is longer lead time than that? Possibly. I mentioned that specifications for liquid transformers are approaching, in some cases, a year, and we've even seen 2 years. Could you get a liquid filled transformer less than that? Absolutely. Depends, again, on the specifications of manufacturer. We had some questions here. What is the success rate for converting a liquid filled to a dry type transformer? Our assumptions would be oftentimes, if it's an indoor application and there are some additional design criteria, there's a good chance you might be able to do that. For outdoor applications, it becomes there's a lot more questions that have to be answered. If it's better to use a dry type versus liquid. The issue is are we talking strictly economic, like, hey, what is my installed cost? What is my cost of ownership? What are my potential liabilities? What are the potential lead times? To say, where you should be focusing to, it really is unfortunately very customer and application specific. We've had some questions on, if there is a method to convert a liquid to a dry type. Typically, we would depend upon our regional sales managers to be able to work with our customers to do that. Our quotations people can give you some advice, but they're not necessarily equipped to be able to understand all of the intricacies with their design. Really, this is best handled through our sales group, working directly within customers to try and evaluate their individual applications. But again, one of the things we're trying to get across from this presentation is that if you do have a liquid filled specification, it is very ineffective. And in fact, in most cases, we'll probably just reject it to give a dry type equivalent. What we really need is we need the end customers to say, hey, I would like to consider a dry type, and here is an actual dry type specification in order for us to do it. And because there are so many site considerations on evaluation, it's not something necessarily that manufacturers such as us is best equipped to do. That really is something that the specifying engineer or end users would have to do. I did have a question here. Are transient resistant transformers available? And I think I understand what you're asking, but that's a very broad question. So if I get a voltage transient, what can I do to have a transformer design that can mitigate that high voltage transient? Well, there's a few different things we can do. First of all, part of that might be what's the BIL, basic impulse level. As we said, for dry type, we can go up to 250 kV BIL, which means we can handle a 250,000 volt spike and shouldn't arc. Okay. Liquid filled, obviously, especially in high voltage applications, can go a lot, much more above that. So that is one method. What is your BIL rate for the transformer, and what is the expected maximum voltage of your transient? Saying that, there's also certain things that we can do. We can add what are called snubber circuits, or we can add latent arresters. Both of these devices are commonly used to help deal with high voltage transients. Now, there's a lot of other considerations with high voltage transients, such as rise time, but there are things that we can do that, especially within the BIL, latent arrestor, and snubber range, that can make dry type transformers very resistant to a number of different transient events. I hope that answers your question. If not, if you can give me more clarification, I'd be more happy to address it. All right, I don't see any other hands raised. I don't see other questions. I'd just like to thank Sumant. I would like to thank all of the attendees for spending some time. Hopefully you found this training valuable. If anybody has any questions, please don't hesitate to contact our sales or marketing group. We'd be more happy to talk to you. And we wish everybody a wonderful day. And again, thank you so much for your time and considering Hammond Power Solutions. Bye, everybody.